Good afternoon, folks. How are you today? We are into lab number 13. In this lab, we are going to solve one second order ordinary differential equation, an initial value problem. You may remember that last week in the previous lab, we solved one first order ordinary differential equation. So here is our problem, a problem that you may remember from your physics or dynamics class. It's about a simple pendulum. We have a particle of weight W that is suspended on a weightless rod of length L. So let's visualize it. We have a rod at the end of which we have a particle that has a weight of W, which we'll write as mg. The length of this rod is L, and this is equal to 2 feet. We are given that the acceleration due to gravity g is 32.2 feet per second square. We'll keep all our units in feet and second. And the equation of motion for this simple pendulum is that the second derivative of theta with respect to time is minus g over L sine theta. So we have theta double dot is equal to minus g over L sine theta. So what is our theta? Theta is the angle this rod makes with the vertical. So if we extend this, this is angle theta. So before we look at initial conditions, let's see where this equation comes from. So in our coordinate system, that is our normal direction, and perpendicular to it would be the tangential direction. So when we let this particle go, the rod is going to spin in this direction. So let's look at our free body diagram. So on this particle, we have this weight force mg, and then if we free it from the rod, we'll have a tension force along the rod of P. So when we look at forces and sum them up in this tangential direction, positive being this way, we will have a component of mg, and it'll be mg sine theta in positive tangential direction. We know this would be mass times acceleration in tangential direction, which we know is mass times rate of change of the velocity magnitude. So let's see, when we have a rod at an angle theta, then when it moves in an arc length, that arc length would be r theta or L theta in this sense. So when the theta changes, that is our velocity. So we know our velocity is going to be L times theta dot. But however, notice when velocity is positive, theta decreases. That means theta dot is negative. So what we need to do is put a negative sign here. So V is minus L times theta dot. So now if we differentiate it with respect to time, V dot, L does not change, so it'll become theta double dot. So what we have therefore is, we have mg sine theta is equal to m times minus L theta double dot. So if we cancel m on both sides, what we will do is we will get theta double dot. well, I already have that. Theta double dot is equal to minus G over L sine theta. So that's our differential equation. Since it's a second order differential equation, what we need is we need two initial conditions. So our two initial conditions are at t is equal to 0, theta is equal to theta 0, so some initial displacement, and we'll just let it go. So our velocity, angular velocity would be 0. Right? So again, let me write down my equation. So we have L theta double dot V dot is equal to G sine theta. So we got theta double dot is equal to minus G over L sine. Okay. Now, if theta is very small, then we can say sine theta is approximately same as theta in radians. So we can say when theta is small, this equation becomes G over L times theta. So notice as we derived our equation, theta double dot was non-linear in theta because we have sine theta on the right hand side. So we will really be solving a non-linear differential equation. However, if we make the approximation that our theta is small, then this equation becomes linear because now you can see theta double dot is proportional to theta. It is linear with respect to theta. Now, if we make this approximation, then we can solve for the time period, and the time period for linear case is 2 pi times length over g. So what we are going to do is length over g. What we are going to do is we are going to solve this differential equation for initial displacements from 5 to 75 degrees in steps of 10 degrees by Runge Kutta fourth order method. We will use a spacing of 0.02 seconds and we will find time period for each of these solutions. We are going to plot the initial displacement versus the time period and compare it to this linear solution. Okay, so please prepare a template like this, and you should have a VBA module having two functions. So remember, option base one means all our arrays, the starting index is going to be 1 instead of the default 0. So here is our Runge Kutta function for second order ODE. So we are going to input h and the previous x, y, z values. It is going to compute the 4k's, k1, k2, k3, k4. Carefully type these equations. This is where mostly people make mistakes. And then this is our new y value, and this is our new y prime value, which we are calling z. And this method, or this function, is going to return this array. Notice this array is a row vector of size 2 only. So all we are returning is y and z values. And then, of course, this is our differential equation that we are trying to differentiate. And notice how we write this equation. We'll write this equation. Theta double dot should be a function of t, theta, and theta dot. which is our minus G over L sine theta. So what we have in this function is we are importing the value from the worksheet named data of G and L. And this is our function. Notice our theta is in radians. So when we feed it in, theta is in radians. Now, we don't need omega here, but to be general, because this function requires function of 3 arguments, we need to have this function having 3 arguments, even though our function is not dependent on omega. Okay, so let me fire up my spreadsheet. Here is my spreadsheet. So I have a worksheet named data. And remember, I have a small mistake in my problem statement, which I will correct before posting it. We are going theta 0 from 5 to 75 degrees in steps of 10 degrees. Okay. So let us start by naming our cells. So this cell we are going to name G. This cell we are going to name L. This cell we are going to name V. This cell we are going to name H. Always a good idea to check name manager, and we have these 4 names. 4 names. All right, let's start putting in our formulas. So T is equal to 0. Theta 0 is this value, which is in degrees. So we are going to take this, multiply by pi, divide by 180. And this is equal to V. Okay. So we are going to take these 2 formulas and copy them across. All right. So that's what we have done. Now let's go to our next iteration. So we are going to increment time by h. And now we are going to invoke our Runge function. So we are going to pass h and then x, which we are always going to pick from column A. So we are going to use function key and just put a $sign before A, comma, then we are going to pick up theta and theta dot. And remember, we are computing 2 cells at a time, so control, shift, enter. And then we are going to take these 2 and copy them across. So we are done, that's all. So notice how easy it is to do parametric study. So now we are going to copy this down to row 112. Okay. So let's see what we want. 2 decimal digits column A and rest everything 5 decimal digits. So format number 2. Okay, take all of these. Format number, and we want 5 digits. Okay, so now I want you to make sure that you check first few rows and make sure you get exactly the digits I am having. You match each and every digits. Now, one of the things we didn't do here is we don't know whether this h is equal to 0.02. How many decimal digits does it guarantee in theta and theta dot? So you might want to check it out. But let's suppose I have at least a few digits correct. So we will check our solution. Okay, so let's go ahead and see what our solution looks like. We'll do it for just our first set. So we are going to plot first 3 columns. Insert XY scatter, and let's say we want dots in everything. So we are going to put this on a new sheet. So this is our motion analysis. Okay, so let's start doing some formatting so our numbers make sense. Format axes, we want it to go only up to 2. We have extra digit, so let's make that 1. Okay, let's see y-axis. So it goes from minus 0.4 to 0.4. So we just need 1 digit here also. Okay, let's put some axes, titles. So about chart. So this is our simple pendulum. Okay, axes titles. So we have time in second. Okay, y-axis. What I want to do is I don't want to put them on different like secondary axes. So we'll just say our theta and angular velocity, which are in radians and radians per second, are on the same axis. Now I chose carefully the values so that they would look nice. Okay, let's look at our legend. And we need to give some titles. So we are going to select data, series 1, edit, and give it a name. So this is our theta. Series 2, let's call it angular velocity. Okay. So what happened here? We need So you can see that our angle, which started at 5 degrees, goes through 0, -5, back through 0, and about here it is back to 5 degrees. So you can see our time period is somewhere between 1.4 and 1.6. Okay, let's also look at angular velocity. So we started at 0, and of course it went in negative direction. Theta dot is negative. So this is our minima, went to 0, maxima, and then when it swings back to its original position, its velocity is 0 again. So you can see when I point it out, I get 1.58 is approximately the time period. So that is what we want to find for every theta 0. Okay. So I would like you to think about if there is an elegant way to find the time period for each theta 0. I am going to do it in a very silly way. Okay. So let me show you the way I'm going to do it. I'm going to just manually find it. So here, notice for 5 degrees, I start with a velocity of 0, and I'm going to scroll down. Again, halfway through, it goes from negative to positive. So somewhere in between it is 0. So it remains positive. And here it goes from positive to negative. So what I'm going to do is I am going to just pick the last positive value. Let me bold it. Let me box it. And I'm going to take 1.56 as the time period. Now, I suggest what you do is you know that the time period is between 1.56 and 58. So you should take it as 1.57 in between. So for your data analysis, make it 1.57. I'm just going to make it 1.56. So now we'll go in the next column, 15 degrees. And I know it should be somewhere around nearby. So again, it is 1.56. And then next it will become between 1.58 and 1.6. I'm going to take the initial value. So before I forget, let me enter 1.56 and 1.58. Okay, let's go 35 degrees. So when we go to 35 degrees, this is the value. So 1.6, then 1.62, and then we have 1.66. And then we have 1.70. And 74. This we just did 74. This was 70. This was 66. What did we have? 606266. Okay, so let's make this all 2 digits. Okay, and then we want to plot these. Again, we'll put it on a new sheet. Call it time period. Okay, and so the x-axis looks okay, y-axis looks okay. We just need to add chart elements. So chart title, time period versus initial angle. Okay. So this is initial angle in degrees. Vertical is our time period in seconds. And that's it, folks. Let's just position these in the order we have done them. And we save it. So file, save as. So instead of template, I'm going to just say demo. Okay, folks. So this is what our plot looked like. Now notice I picked up the lower time period value. If you pick up the midpoint, the curve might be smoother. But notice when you calculate 2 pi L over G, the time period. So let's calculate that theoretical time period. So it'll be 2 times pi times square root of L over G. Oops. Let's cut this out. That's our time period. Let's put this formula here. So you can see 1.5659 is our linear time period, irrespective of initial angle. But we see that it depends on initial angle when we consider the nonlinear solution, right? So this time period is only good when our initial displacement angle is small. Once the initial displacement angle becomes large, the linear approximation is not good. Okay, folks, so I did my time period estimation in a very silly way. Can you develop a formula or a technique that is elegant to find time period for each initial displacement? So I would like you to put in a text box or give me some idea and see if you can figure this out. So here is our grading rubric. And please check all your formatting. Make sure you have grid line, row column headers. You don't need to fit the table into a single page. You can leave whatever is the default setting, file name, submit it to the Dropbox. Okay, have a good day.